Okay, let's take a look at number 3 in sample exam 2, Chem 11. This is yet another question about gases, specifically gas stoichiometry. And this is actually a fairly complex question. What the question tells you is you have a metal ore. Anytime you see the word ore, it always means that there's a couple of things in it. It's basically something that has metal and metal oxide, some combination of those things. And so this one is composed of a mixture of two things, magnesium oxide and strontium oxide. So the way you want to visualize this thing is that you have this ore and some portion of that black is going to be magnesium oxide, and then the other portion of it, and color that green, is the strontium oxide. And we don't know how much is each one, but when you weigh it, you find that this whole thing is 2.747 grams. And then you mixed it in with CO2 in a container, and they undergo some kind of a reaction, and product at the end is some magnesium carbonate, and then you also have some strontium carbonate. It also tells you that some of the CO2 is left over. So this is at the beginning, right? And then this is at the end. So the question then is, what's the mass percent of magnesium oxide in the original ore? So what's the portion that's the black part right here? Percent magnesium oxide in the ore can be calculated if you take the mass of the magnesium oxide over the mass of the ore times 100%. Now, we know the mass of the ore, so it's just a matter of finding the mass of the magnesium oxide here. Now, that's actually not that easy to do because we have two things that are unknown, right? The magnesium oxide and the strontium oxide. Given that we know there's a reaction, you can tell that you would have to do some kind of stoichiometry with the CO2, and so we have to write some reactions. One of the most common mistakes in a problem like this is that students end up just writing one reaction, and they would write a reaction that looks like this. MgO plus SRO plus CO2 goes to MgCO3 and SrCO3. And the reason this is wrong is because to produce MgCO3, you don't really need the SRO, right? Because there's no Sr in that formula. To produce the SrCO3, you don't really need the MgO. So there's no Mg in that formula either. So really, this is not one reaction that occurs, but actually two different reactions. And the reactions are, one, just between MgO and CO2, forming MgCO3. Then the other one is SRO plus CO2, forming SrCO3. And that's what we have to use to help us figure out what is the mass of the original MgO. I can figure out the mass of this if I somehow know how much CO2 reacts with it, okay? But the problem is I don't know how much CO2 reacts with it. I was just told that some CO2 reacts with both of them, and there's some leftover CO2 in the end. So one of the things that we can figure out first is how much CO2 is being used to react. To do that, I can just take the difference in the amount of CO2 I have at the beginning versus what I have at the end. So pressure of CO2 used in reaction with both of those oxides would be just taking the 670 torr, which is what I started with, minus the 180 that I'm left with at the end. I'm going to just convert this to atmosphere because I'm going to need to use the ideal gas equation at some point, and that would give me 0.6447 atmosphere. So this is how much CO2 is actually used in the reaction with both of the oxides. Now we have to think about how to bring in mass here of the two different oxides. Whenever you have a situation where you have a total and you need to know the component of each one of them, this is a good time to use algebra to solve the problem. So let X be the symbol for the mass of MgO, and then the total, which is 2.747 minus X, then could be the symbol for the mass of the SRO. Now we can use those masses as a way to calculate the number of moles, right? Now, why do we need number of moles? Because we know that this oxide and the carbon dioxide react with each other, so we're going to have to get some number of moles calculation here. So the number of moles of MgO is just going to be its mass, X in this case, divided by its molar mass. So it's 40. And so this is just 1 over 40 times X, and 1 over 40 is just 0.025X. So this is the number of moles of MgO. You can see where I'm going with this because once I know the number of moles of MgO, I can calculate the number of moles of CO2 that reacts with MgO, right? So number of moles of CO2 that reacts with MgO, I can use this number of moles that I just calculated, 0.025x, and I can just multiply this with the one-to-one relationship between MgO and CO2. So that means this is the number of moles of CO2 that reacts with my MgO. Let's calculate the second oxide, which is SRO. We can calculate the number of moles of SRO by taking its mass, 2.747 minus X, and then we divide that by its molar mass, which is 104. I can plug this in my calculator to get these two numbers right here, 0.0264. That's if I just take 2.747 divided by 104, and then minus 0.009615X. That's the number of moles of SRO, which allows me to calculate the number of moles of CO2 that reacts with SRO. And since SRO also has a one-to-one stoichiometry with CO2, we end up getting the same expression at the end, right? 0.0264 minus 0.009615X. I'll skip the units here, but you multiply this by one-to-one mole ratio and you end up getting the same thing out here, okay? Both of these numbers right here is the number of moles of CO2 that reacts with each of those species. And so when you add them together, that equals the total CO2 that reacts with the ore. But we can figure out what that total CO2 is because we know the pressure of the CO2. It's given in this number right here. So then we can use our ideal gas equation. So we want to get the total number of moles of CO2 that reacts with ore, right? And we do that by using PV equals nRT or solving for N, which is just PV over RT. The P is 0.6447 atmosphere. Again, I'm skipping units here. 1.25 is the liter. R is 0.0821. And then temperature in Kelvin is 303. And when I multiply all that, I get 0.032397. Okay, that's the mole of CO2. So the number we just got here in blue is the total number of CO2. The number we got earlier in red is the totals of CO2 that reacts with the ore too, but in terms of coming in from each oxide. Now, of course, these two numbers are supposed to be equal to each other. So what we can do now is let those two expressions equal to each other, and then since we only have one variable in it, we can solve it. Okay? I'm going to say 0.025x plus 0.0264 minus 0.009615x. That's the sum of those two things in red. They should equal 0.032397, which is the thing in blue. And we can then isolate the x and then solve for our x value. Okay? And so 0.01538x should equal to 0.00599, and then the x itself would equal to 0.3898 grams. And remember what the x represents is the mass of MgO, right? Now that, by the way, is not the answer, right? Because what we're asking is the actual percent mass of MgO in the ore. So that's complete our calculation here by doing that. 0.3898 grams over the mass of the ore, which is 2.747 grams times 100%. And that gives us 14%.